Okay, so we are now going to talk about something else in 3 dimensions, the magnetic force on a charged particle moving through a magnetic field. So I have a very small magnet here, but pretend that this close side to us is the north pole of this magnet, okay? And that a charge is going to zip by very close to this magnet right here. It's going to zip by this way, moving to our left, and this is a north pole. A north pole creates a magnetic field that points, the man has decided to have the magnetic field point away from the north. So the magnetic field lines are coming this way towards the south, the back side of the magnet, if the back side were the south. And if this is the north, they would be pointed this way, okay? And they would actually loop around this way. But if we're very close to this, they're pointed right close to the middle here of this north pole. It's zipping by right this way through the middle, through the center dot there. Then the magnetic field lines are pointed this way, which is towards us. Okay, in my room, that's going to actually be south. Up, it's hard to see this, but up is up, down towards the ground. In my room, west is to the left, east is to the right. North would be, if you imagine from above, if west is to our left, north is away from us, which we draw with X's. South is towards us or out of the page. We draw with dots, like there's an arrow, like a bow and arrow. The arrow, that's like the arrowhead pointed at you. And the X's are like the tail feathers of the arrow pointed away from you. If an arrow were shot away from you, you would see the X of the tail feathers. So what I'm going to do here is I've made a little diagram for us in 3 dimensions. And let me set it up here. This is we're going to do actually I have it all upside down. Let's go that way. That's better. So we're going to do the equation for the force on a charged particle. So this is going to represent my charged particle. My charged particle for this problem, I don't know, you probably can't see this, but it's plus, you can't see it. It's a plus charge, okay, moving to your right, okay. Actually, we had it moving to our left, so I'm going to spin it around here, and I'm going to change the problem because I have the papers like this. So I'm sorry, I had that magnet. I'm going to have the charge going this way, so page right, okay, which happens to be east in my room. The magnetic field lines are pointed this way, okay? They're going to be pointed out of the page at us, okay? So if you have a charged particle that is moving through a magnetic field, there is or can be a force on that charged particle according to this equation. The force on the charged particle. So this is the force on Q, the charged particle. It has to be moving through a magnetic field. The force in newtons will be equal to the charge in coulombs times its speed in meters per second times the strength of the magnetic field measured in Teslas, and then times, and some books leave this out, but it's really times the sine of the angle. And the angle is between these two, between the velocity and the direction of the magnetic field, okay? Many times they make the angle between them 90 degrees, but they don't have to be, and I'll show you that. So this is the strength of the force, okay? It does not give us the direction. This takes care of a lot, okay? It gives us the force on this charged particle that is moving through the magnetic field. This represents the direction of the gray sticks, represent the direction of the positive charge. It's going to be moving to our right. This represents the direction of the magnetic field, okay? So that would be the direction of V, is to the right. The magnetic field is out of the page towards us, which in my room happens to be south. And then the force, what direction is the force? This is just a magnitude equation. So to get the direction, I'll start with this. The force is always perpendicular both to these yellow sticks and to these gray sticks. Okay, always, no matter what we do, no matter how we turn this around, the force, which I'm going to represent with the red sticks, always has to be perpendicular to both this, the direction of the velocity, and the direction of the magnetic field. So if I were to go like this, right, if the magnetic field could be anything like this, if these guys, the velocity and the magnetic field, are in the plane of the page, it doesn't matter what they are or what directions they are. The only direction perpendicular to both of these directions is out of the page or into the page. Those are the only possible directions that are perpendicular to both. And we have found that the magnetic force on a moving charged particle moving through a magnetic field is always perpendicular to both the velocity of the charged particle and perpendicular to the direction of the magnetic field itself. Okay, so in this case, we had the object moving to the right. Page right. So you imagine this is our page. So it's moving page right. The magnetic field, and I only have a few sticks because that's all I can really get to sit on here and stay. But the magnetic field is pointing this way, okay, out of the page at us. And there's more lines than these. There's a whole bunch of dots coming out of the page at us on this side and this side. There's a pretty uniform magnetic field. And so here comes the charged particle, and it's going to our right. The magnetic field is out of the page at us. The only two options, the only two directions that are perpendicular to both to the right and out of the page are either up or down. Okay, those are the only options. So I really, really encourage you first to narrow down your choice of the direction of the force to those two options. There are only two options for every problem, for each problem. So if it's a positive charge moving to the right and the magnetic field is out of the page at us, there's only two options, up or down. A negative charge will get pushed the opposite direction. Whatever we get for the plus, the minus will be in the opposite direction. So we're going to do some problems first with a positive charge moving. So we'll do that. If the positive charge is moving to the right, okay, and the magnetic field is at us, it turns out the force is indeed up. Okay, and there's a math equation that would give us that answer, but it's way more complicated than we need. We already have the magnitude of the force. If we just want the direction, we can use our right hand. Okay, there are several different right hand methods. I'm going to use this one that I found is most commonly used and can be used for the most different types of problems when you get farther on in math. And there are other things you will learn that also use your right hand. I found most people using the one I'm going to use. Okay, so you first take your whole arm and your hand, and think of this particularly your pointer finger. Point it in the direction of the velocity. So you start there. Okay, Q is not a it is not a vector. The velocity really is a vector. So start with V. What direction V really is this way. Okay. Then when you take your hand like this, you need to be able to bend the rest of your fingers like this. Okay. And you can turn your arm around. You can twist. All right. You can rotate. But what we want to do is we want to end up with our fingers pointed in the direction of these yellow sticks, the magnetic field. So I need my fingers pointed this way, okay? And you can turn your arm around and go like, say, this. Okay, you could do this if you really want. It doesn't matter. Okay, so V is this way. I bend my fingers such that my fingers are pointing in the direction of the magnetic field. And see, my thumb points down. So I messed it up. The force is not this way. The force is this way. The force is down. Okay? So V is this way. Magnetic field is this way. The force is down. Okay? So narrow it down to up or down. Let's try another one. What if the velocity were still to the right, but the magnetic field is this way? Okay? And it's kind of coming that way in the screen, if you can see that. It's a little hard to do in 3 dimensions. So V is still this way. V is now going to be like this. I'm going to bend my fingers past 90 degrees. So we plug in a number bigger than 90 degrees there. Like this. And the force will be still down. Okay? In fact, if the magnetic field is anywhere between here, like, bigger than 0 degrees and less than 180 degrees, if the magnetic field is anywhere over here, I'll start here with V. The magnetic field is there, doesn't matter. The force is always going to be down, but not the same magnitude. It will be directed downward, but as this angle changes, this magnitude will get bigger, as the angle gets close to 90, and then less and less and less force until you get just to 180. If the magnetic field and the velocity are parallel, whether the velocity is this way and the magnetic field is this way, or that's kind of anti-parallel, or if they're in the same direction, if you plug in 0 or 180 to sine of theta, you get no force. So if the velocity and the magnetic field are parallel, doesn't matter what directions they are, there is no force. Okay? Let's try another one. Let's have the velocity go up and the magnetic field come out of the page at us again. So V is this way. So you take your hand and you stick it this way, take your pointer finger, stick it that way, and your whole arm goes like this. Okay? No fair, by the way, moving at the wrist. You do not move at the wrist. Imagine you have like a wrist brace on. I should go get a wrist brace. So stick your fingers like this. Okay? And then you're going to bend your fingers, but you want them to point not away from you. You want your fingers to point at you. So you can go like this. You can turn your whole arm around. That's fine. You can go like this. That still works. V is this way. Magnetic field is out of the page at us. And you'll notice my finger is pointing to the right. Okay? So, or like this. Doesn't matter. So the force is to the right. The direction of that force. Okay? To the right. Let's try another one. Suppose it's like this. Suppose the magnetic field is, let's have it like that. Okay? The velocity is this way, and the magnetic field is, you stick your fingers this way, all your fingers that way, point that way, along the direction of the velocity, and we're going to bend our fingers such that they're pointing straight up at the sky. Okay? So you can turn your fingers around, turn your hand around, don't bend here, but like this. Okay? And you can orient your whole body. You can turn the rest of your body however you want, whatever's comfortable. And you go like this. And my thumb is pointing away from us towards the wall here, which in my room is north. But we would draw X's. The force is away from us, which means as this particle goes this way and gets pushed this way, it's going to start to turn. But when it starts to turn, yeah, well, we'll get into that. We'll get into that later. So let's try another one. Let's have the velocity coming away from you. All right? So the velocity, you can't see it probably very well. The velocity is going to be going this way. Still positive charge. So the velocity is going this way. So stick your hand towards your computer screen. Okay? Away from you. Okay? So stick your whole arm like this. The velocity is going to be like that. And then we want to move our fingers until they point in the direction of the magnetic field, which is up and to the right. Okay? Which is, east and up in my room. But don't worry about that. Page, up and to the right. So you take your fingers like this and you turn them around either like this or like this, whatever you need to do to get your fingers pointed up and to the right. And your sorry, I should have done this first. What direction is perpendicular to both into the page and that way? It's either up and to the left or down and to the right. So it's either this way or this way. We stick our hand this way, our fingers point this way, our thumb points down and to the right with our right hand. So the force on a positive charge will be down and to the right. Let's make it a little easier. Let's have the velocity going away from us, but now the magnetic field is to the left. Okay? So the velocity is away from us. Stick your hand into the computer. The force is still given by this equation. The magnitude of the force is still given by this equation. But we're finding the direction of the force. So what direction is perpendicular to both? I have it like this, I think. This way. What direction is perpendicular to both away from you and to the left? It's either up or down. So we stick our right hand into the page, and we turn our fingers, we rotate around until our fingers point to the left. So going like this, we want our fingers to be able to point to the left, and just bend at your knuckles here like this. Just bend like that. So it's like, there's my fingers pointing to the left. See the magnetic field? These fingers point to the left. My pointer finger points away from me. My thumb points up. So the force is up. Okay? And we'll do some other problems, on a screen. We could do that. But I'm going to tell you one more thing here. Reminder, if the velocity and the magnetic field are parallel or anti-parallel, no force. What if it were a negative charge? Okay? Well, we just figured out that if the magnetic field is pointing to the left and the charge is moving away from us, the force was up. A minus charge always gets pushed the opposite direction. So you have two options. And I'm going to let you pick whichever one you want. Some people find this the best. They say, I always want to use my right hand every single time. I'm going to use my right hand. And if it is a negative charge going this way, I will flip the answer at the end. So I will solve as if it is a positive charge and then just change the direction at the end. So the velocity is going away from me. The magnetic field is to my left. The only options are up or down. I will use my right hand, spin it around until my fingers, which are the magnetic field, point to the left. The force is up on a positive charge, but it is a negative charge, so flip it. The force is down. That's what some people do. Some people say, and I actually have, the second way has grown on me. At the very beginning, you have to check, is it plus or is it minus? Don't forget the first step. The first step really is check to see in the problem, is the moving charge plus or minus? Because it will give you a totally different answer for the direction. So I think it's better to look first. Is it plus or minus? If it's plus, right hand. You can use the right hand and switch if it's minus. If it's minus, I would suggest actually, I like the second way better, use your left hand. Okay? So if I were to use my left hand and the velocity is still away from me, I point my fingers this way, my whole arm this way, okay? And then when I bend my fingers at the knuckle, like this, I need my fingers pointed to the left we had. So I need my fingers here not to point down. See how they're pointing down towards the ground? I need them pointed to the left. So I rotate my arm around like this. My fingers are pointed to the left and my thumb points downward. Stick your thumb straight out. My thumb points downward. So that's the same answer we got before. If it were a positive charge, it got pushed up. If it were a negative charge, it gets pushed down. I hope I did all of those right. I think I might have made a mistake in there. I'll have to go back and look. Let's try another minus. Let's say the minus is moving down, okay? And the magnetic field points out of the page. So the magnetic field is pointing out of the page at your eyeballs. This points this way, but we're going to change this to a minus charge. I would suggest using your left hand. This one's not going to be... so my left hand needs to point straight down. I need to turn my hand... Sorry, it's going to be like this. Pointing down. I need to turn my arm around until my fingers point to the... I think I had it left. No, out of the page, I said out of the page. So fingers point out of the page, towards our eyeballs, towards your screen, or out of your screen, so this way. Okay, so they point like this, and the force is, I'm using my left hand, it's a minus charge. The force is this way to the right. Okay, if it were a positive charge moving downward, and the magnetic field were out of the page, the force would be to the left. Okay, so that's how we find the direction. I know that doesn't sound very easy. It's actually much easier than assigning directions and using vectors and using something called a cross product and a determinant. It gets a lot of math for just finding us the direction. So first thing I would suggest you do, number one, always narrow it down to two options. What direction is perpendicular to page right and page up? It's either towards you or away from you. What direction is perpendicular to towards you and up? Page up. It's either to the right or to the left. Okay, so narrow it down to those two options. A positive charge will get pushed one way, like if we said towards you and up, the positive charge will either get pushed right or left, and the minus will get pushed the other way. So do that first. Narrow it down to two options. Then, is the charge plus or minus? Look at that next. Then pull out your right hand for a plus, okay? And then if you want to, you can switch that answer for a minus, or pull out your left hand for the minus charge, and you stick your fingers in the direction of the velocity. So if the velocity, again, one more time, if the velocity is to the left, okay, and the magnetic field is up, okay, so the velocity is to the left, I'm going to do a positive charge. The velocity is to the left, stick your whole arm to the left. I need to bend my fingers, and right now they're going into the page. I don't want them into the page. I want them towards the ceiling. So I could rotate my hand around like this and bend them towards the ceiling. Bend them towards the ceiling, and the force is into the page. My thumb is pointed away from you. I could also do it like this. That's probably easier for me down here. V is this way. B is towards the ceiling. My thumb points away from us. For a minus charge, V is this way. And I need to bend my fingers, stick out my thumb, bend my fingers so they're pointing towards the ceiling. We said the magnetic field was towards the ceiling. Point them around this way, and the force is towards us for a minus charge. So out of the page, which we draw with dots. Into the page, we draw with X's going away from us. So I actually got out a wrist brace here. Sometimes when people solve these problems, they kind of bend at the wrist and they get all messed up. So the first thing you do again is if let's say the charge is moving upward and the magnetic field is toward you, the only options for perpendicular to both up and towards you are either left or right. And so if it's a positive charge, you stick your whole hand this way, page up. And I'm going to turn my hand around, and see, I can't bend at my wrists now. This wrist brace is keeping me from bending at my wrist. Okay, so stick my whole hand like this, and I need to turn my fingers until they point out of the page, away from your screen. Okay, and I've got it like that, so the force would be to the right. Okay, so you cannot bend at the wrist. Take your whole hand, stick it in the direction, your whole arm here, from elbow to first finger, stick it in the direction of the velocity. Bend your fingers however they need to bend. You know, they might bend like this, might bend like that, might bend like this, or rotate this way, or that way, or rotate this way to point them to the right, which is, let's say the magnetic field lines point to the right. That would be like this. The magnetic field lines are pointed to the right. The velocity is up. I can either do this, take my fingers, point them page up. My magnetic field points not out of the page, but to the right. So now my thumb, you see my right thumb is pointing away from us. So that would be X's. Or you could do it on this side. It doesn't matter. Take your fingers, point them up. The magnetic field points to the right. And your thumb points into the page X's. Okay. Of course, the same thing is true if it's a minus charge, but I would suggest using your left hand. So first thing, determine what direction is perpendicular to both. So if this is up and this is page right, the only directions that are perpendicular both to up and page right are out of the page and into the page. That's number one. Narrow it down to the two directions that it could possibly be for your problem. In this case, out of the page or into the page. Secondly, is it a positive charge or is it a negative charge? If it's a positive charge, you can use your right hand. If it's a negative charge, you can use the right hand and switch, or I would suggest actually going to use the left hand if it is a negative charge. Students often forget to look to see if it's a negative charge or not. So I would want you doing that early. You stick your hand in the direction of V, spin. When you bend your fingers, you want them point in the direction of B, and your thumb points in the direction of the force, of the direction of the magnetic force on your charged particle moving through your magnetic field. Remember, the angle is important. If the velocity and magnetic field are parallel, then there is no force. And now we're going to try some practice problems off of a screen. So here are the notes. The direction of the magnetic force, FB, but magnetic force, is found by the right-hand rule. And I'm calling this right-hand rule number 1. We learned number 2 first. You point your arms and fingers in the direction of the velocity. Then you orient your hand. You spin around without bending your wrist so that you can bend your fingers at the knuckles in the direction of the magnetic field. Your thumb points in the direction of the magnetic force on a positive charge. A negative charge will have a force in the opposite direction. You can use your left hand or use the right hand always and switch the direction. Just don't use the left hand for a positive charge. Remember the order. You stick your hands in the direction of V, then you bend your fingers in the direction of B. Like in the equation, it was Q, V, B. V comes first. So V, then B. Your thumb points in the direction of the force. Okay. Remember, the direction of the force is perpendicular to the electric charge's motion, the velocity, and the magnetic field. So find the two directions that are perpendicular to both first. Okay, now we're going to do a problem here. If a arrow is in the plane of the page, we just draw it in the plane of the page. So an arrow up, we draw up, down, we draw page left, we draw page right. So here is a problem. The problem has a magnetic field that points to the right, and it looks pretty uniform because these lines are equal distance from each other. Okay, they're not closer together someplace and farther apart someplace. And these lines are pointing page right, but also imagine a bunch of lines identical to these closer to you than the screen, also pointing to the right. And there are lines pointed behind your screen, pointed to the right. And through this magnetic field comes zipping a positive charge, zipping page down. Okay, and we're going to find the direction of that force. So the equation for the force would be Q, whatever this charge is, Q naught, V times B times sine of 90, because this is perpendicular. See how this is perpendicular? Page down is perpendicular to page right. Okay, but what direction is this force? First, figure out what are the two possible directions. What directions are perpendicular both to page down and perpendicular to page right? The answers are towards you and away from you. So out of the page towards you and into the page away from you. So let's use our right hand. You're going to take your fingers and stick your hand straight page down. So let's stick our hand page down. The magnetic field was to the right. So when I bend my fingers, they're pointing away from us. So I need to turn my hand around so they're pointed page right. And my thumb points towards us, out of the page. So V was down, B was to the right. So the force is towards us. I could also show you over here, same thing. V is this way. Turn your fingers so B points to the right and your thumb points out of the page at us, which we draw with dots. So we're going to draw a dot. The force is towards us. So it's we would draw this force like this. We'd put it near the charge and sometimes I draw a circle around this dot so that somebody realizes, hey, that's the force, and the force is out of the page at us. Okay, and we could look at some other problems here. We could do these, but I'm gonna start us with a couple of them. And in this first problem, let's look at this first. The velocity is up and to the left. The magnetic field is page up. Okay, so this is page up and to the left. The magnetic field is page up. What directions are perpendicular to up and to the left and up? Okay, if these are in the plane of the page, which they are, both of them are in the plane of the page, then the magnetic force will have to be out of the page towards our eyeballs or into the page away from our eyeballs. So what I'm going to do is the charge's velocity points up and to the left. And we need to bend our fingers so that they point upwards towards the page up, and the magnetic force is going to be into the page. So we're going to get something that looks like this, an X near there. The next problem has the velocity going to the right. So if the velocity is going to the right, and the magnetic field is out of the page at us. So I can do it like this, I guess, probably better. V is to the right. The magnetic field is out of the page. So we need to turn our fingers around this way till they're pointing out of the page. And our thumb points downward. I'm sorry, I should have said both of these are positive charges. If you look at the problem first, what two directions are perpendicular to the right and out of the page? The answers are page up and page down. So we said V was this way, B was that way. We get page down. It is a positive charge. Next one, the magnetic field is going, the velocity is going page up, and the magnetic field is X's away from us. So what directions are perpendicular both to page up and into the page? It's right or left. Okay, so it's either right or left. This is a minus charge. If you look at the charge there, it's a minus Q naught. So I'm gonna choose to use my left hand. So my V, my fingers straight up. My magnetic field needs to point away from me when I bend my fingers, so turn them around till they're like this. The wire's catching. Magnetic field is into the page, and my force is to the right. Okay, V is up, B is away from us, force is to the right. And the next one, it is a negative charge, but this is a trick. Okay, it's a negative charge, V is to the right, B is to the left. You could do this, but see, no matter what I do, I could have any direction because the force is zero. They're anti-parallel. The the velocity and the magnetic field are in opposite directions. There is no force. That angle is 180. There's no force. So you could come up with any direction. It's kind of like saying, hey, look, there's no force on me. You know, what direction is that no force? Up, down, left, right. It doesn't matter. And we'll worry about the last problem at a later date. It's going to be working in reverse. They give you the velocity and they give you the force, and they really should say, if the magnetic field is perpendicular, what direction is that? But we could we'll do that one another time.